Thank you for joining us. We've got some special guests here over Discord, and we're going to be talking about bolts and welds today. So this is kind of like the connections topic bundled in one, partly because the assignment video was released last week instead of bolts, partly because I didn't have my notes prepared yet for welds, but now they're ready. So yeah. Basically, within the connections topic, right? Actually, let's start even more overall, right? We have members. We have member design. Maybe that should go above because that's arguably more important to begin with. Member design for steel, right? And then that's where you do everything like your flexural checks, your shear checks, compression, tension, all these things, right? And we've kind of ticked through all these things now. We kind of know them, right? Connection design is a little bit different, right? So connections is basically how two members are connected. It's kind of more like a later stage design thing, I guess you can say. It's just as important, but how members actually link together and are physically manufactured, like physically assembled, that's quite important, right? Because that's how you actually end up building it. So to do this, we have bolts and we have welds, right? Bolts are generally cheaper and are easier to assemble. It's like you have a little you have your blueprints, right, which is like the same as like a Lego instruction manual, basically, just to be able to assemble things with bolts. With welds, it's a little bit harder, unless you can prefabricate it in a factory, right? So sometimes you have these big members, and then like plates and things like that can be pre-welded so that you can bolt things together, and that's done in a factory. That's completely fine. For welding on site, that's actually quite difficult, and you try to avoid it as much as possible. But welds, they essentially develop as strong of a I don't know, I'm finding it hard to explain this. So you have two members, right? So you have two square hollow sections. This is like kind of a weird example, like that, and then the other one's kind of like linking up to it. You can weld around the entire edge, and it's as if it was one square hollow section, right? The weld kind of fully fixes this connection. It has like full rigidity and everything, right? For bolts, a bolt by itself is a pinned kind of connection until you have enough that it locks it in place, basically, right? Yeah, anyway. So within these types of connections, we do two types of design, right? We do shear, shear and axial, specifically tension design. For welds, we just deal with shear design in this course. That's not to say welds don't take on axial forces and whatever, but in this course we just deal with it like that. Shear we call in plane loads, and this is also in plane, and axial design is out of plane. Okay, now I'll explain that in a second. Maybe I'll just draw up some examples. So say you have a frame like this, right? And you're trying to prevent wind loading on it, right? And so you might want to do something like this where you have bracing on it, right? So if we zoom in on the bracing, you might find that this piece of bracing can't fit on the truck because it's too long. So they might want to let's take a step back for a sec. In the middle here, we might have a way to interlock these two members in shear, in kind of a shear connection, right? So it might look like this, right? Now that bolt that I've drawn here in the middle, let's zoom in. That bolt is in shear, right? Because if this force is acting on it, I might draw it kind of from the other perspective. So it's an eye looking at it. It might look like this somewhat. Okay, that's a bit trippy because it's an X, but like that's your bolt. It has the shank with the threads, and then connects up to a washer, right? Something like that. Yeah, if there's tension or compressive forces here, axial forces acting, the bolt is in shear because this is essentially wanting to shear like that, right? So we say that that bolt is in shear because the bolt is perpendicular to the members. Does that make sense? I just want to make sure I'm not just saying fucking random shit.
No, that makes sense.
No, that makes sense.
Okay, fantastic. All right, good.
Makes sense.
Stay with me. So next we'll talk about axial bolts. So say we're designing a warehouse, right? So up the top there, that's the roof of the warehouse, and this is called rafter beams, and they're attached to these columns, and this makes up one portal frame, which this is called a frame, right? Now, okay, you know how for a second I was trying to explain something here? Imagine that these rafter beams are quite long, right? Say this entire, say here is like 20 meters or something, right? And on a truck, right? I'm gonna try to draw this. On a truck, this isn't a very accurately drawn truck, but these members can only be max 15 meters, something like that, right? So they have to be less than 15 meters. So if you want to basically connect up this big ass portal frame, you want to essentially put multiple members on the truck like that and find a way to connect them together, right? And so let me just draw that there. That will, that's the bottom of the page. That might look something like this. I'm going to draw a perspective drawing. And these say the I-beams or whatever, right? Like that. It's an I-beam. That continues. And we have these bolts, right? These are axial bolts. Here, and there's some on the other side, but can't see them, right? And then they have also got like a nut basically on the other side, which locks it in place, right? It's something for the threads of your bolt. That's the threads of your bolt. It's something for the threads of your bolt to bite onto, and you twist it, tighten it, and yeah, so that's the nut. So your bolt, those are your threads, right? Okay, but do you see how they're axial bolts? Because they're basically, when you tension them, right? You tension them by tightening them, right? And then they kind of compress, I guess, and lock it in place. So that's kind of like the definition of an axial bolt. And then it develops this, it's called a moment connection, as opposed to a pin connection. And so this essentially acts as one member, and you can treat it like one beam across that rafter when you do those kind of connections along here. Right. Okay. Does that make sense? So,
Yeah.
Yeah. Cool. Shear bolts, axial bolts. Yeah. For welds, I'll just show you what like shear on a weld might look like. So say you have a column. This is one of the example questions. And we have this plate like that we weld onto it like that, right? And we have let's just say for whatever reason we have this plate, this rectangular plate sticking off this column. If we apply a force like this, right, it's going to cause this weld at various points to want to shear, but in like different directions. Kind of, there's a moment portion of it, and then there's a force point of it, but all of these points in the weld are shearing, right? So that's what a shear weld connection looks like. Does that make sense?
Yep. Yeah.
Vina, you said I don't know.
Oh, yep, it's all good. I was just confused because does the weld stick out like the plate?
Oh, okay. So if we look at this side on like this, it might look like that's your column. So that's a UC, and the plates would come out like that, right? And then the weld kind of has this fillet shape. I kind of just drew it on top, but yeah, it would probably more be like, probably more be like that. Yeah.
Yep. Okay.
Cool. Any other questions?
Actually, yeah, one last question. In terms of the weld, so you see how it's like on the three edges of the plate. Would it be also underneath the plate?
Yeah, you're right.
Like the weld attachment?
Yeah, you're right. I think what I did by accident is I did a cut like that. So that's what that would be. So it would only show that part of the weld. But based on what I drew, which you're right about, it should be, yeah, like that.
No, as in like underneath the plate as well. Do you see like the bottom bit? So you know how there's like three sides attached to the plate. Is there potentially one other side as well? So
on the back?
Like, from the bottom? Yeah, on the back. Do you know what I mean?
Yeah. I know what you mean. You could. I feel like it would be overkill. I feel like it might be overkill. Yeah. I mean, it all depends on the numbers. Like, there's nothing that specifies that you have to weld every edge, which is kind of adjacent. Like, you're talking about this, right, Karan? You're talking about if there was a bit of welding on the back, right?
That's the point I was referring to.
You could do that. I'm just thinking it might be unnecessary. It might be like diminishing returns on that, and it might also take longer just because if this is like a repeated kind of I guess detail around a warehouse, for example, it would be quite time intensive to do something like that, I think. But I don't know. It depends. That's the answer. But yeah.
All good. No, that's all good.
Any other questions right off the bat?
Nope, all good.
Fantastic. Okay, let's talk about, so when I show you this and when I show you this, what, like, just have a guess on what that means. Oh, actually, it's right there.
The design?
You've seen these numbers. I mean, these variables before, though, right? Earlier in the course.
Yes.
Almost.
Yeah.
V stands for shear, right? NT stands for tension, right? That's what we're designing for. And so, we have the exact same thing for bolts. Lockie, do you remember that time we did the recording for this and then it fucked up? I found out what this means. Another word for a bolt is a fastener. Alright. It's kind of like an umbrella term for bolts, nails, just shit like that, right? So when you see F, it refers to for a bolt, right? So N star, what am I saying? V star, right? That would be for a member. But once you add in an F, that's for a fastener or a bolt, right? And you'll see below, not below, you'll see for the week 9 notes, V star W means the shear on a weld, right? It'll be more like this actually for that one. But I'll explain it later. Okay, cool. I want to make a comment quickly, right? So, do you remember how, let's just say for the shear topic, right, for members, essentially, this part was relatively easy to find, yeah, like in your workshops or whatever, right? It's just from the shear force diagram for a member, correct? And then this is where you have to go through like AS4100 and like the code and through the aids, right? Yeah. And so it's a bit different for bolts, because for bolts it's the other way around. This is actually the thing that becomes hard to find, and the capacity is quite easy to find actually. It's just a matter of looking at a table which has design values already on it. So that's what to expect. Let me show you what this ends up looking like. I'll just quickly talk about these as well. Will I? I don't think I will. I'll talk about them when we get to it. So, yeah, we have this table here, and you can just see that like as the number goes up, the bolt grade, that's representing the bolt grade essentially, right? And you can imagine that means it's a stronger bolt. It can take on more, it has more strength basically, right? So we have grade 4.6 bolts, 8.8 and 10.9, which isn't in this course. So it's just to do with the amount of carbon in it. I just had a really bad feeling I'm not recording. Okay, no, we're good. Alright, we're good. So we use ultimate strength in the formulas, not the yield strength. This is for shear, and this is also for tension. Now, for members, we only ever used the member ultimate capacity for the case of tension, and specifically the fracture on the net section. So we use it here partly because I'm kind of just theorizing, but for members you want to be a bit more conservative because there's only one member, right? But for bolts, like this is just from my understanding, since you have bolts kind of acting in parallel to each other, you're allowed to use the ultimate strength, if that makes sense. There's kind of like if one of the bolts fails, or like quote unquote yields, right, it's not the end of the world because the other bolts kind of assist it, and then they reach a point past the yielding point, if that makes sense. Yeah. Anyway, maybe I'll just quickly draw a curve for this, but yeah, it would look something like this, where that's the yield point, and then together the bolts will reach the ultimate point because they're acting in parallel, I guess. So next we'll talk about methods of installation. So the snug, tight, and fully tensioned. Basically, snug tight means you can't loosen the bolt with your hand, right? You've twisted it so much that, like using some kind of tool, right? Could be a wrench, could be whatever, a power tool. You've twisted it so much that it can't be loosened by some dude, right? I think in the code it says like, cannot be loosened by hand by 100 kilogram male adult or some shit like that, right? It's like very specific, but yeah, it's just saying like by a tradie, it can't be loosened. So for a fully tensioned case, you get it to that point and then you keep going, right? So to the point where this part in the middle yields. So here we actually want to encourage yielding because then there's more compressive strength. Oh, sorry, not compressive strength. There's more compressive force because you've over-tensioned the bolt essentially, and it has like a tighter grip, and it won't loosen as much over time, right? So this is important for, if I go back to those examples I was talking about earlier, This is important for axial connections because if you can imagine, if this was just snug tight, this is a really important member in our warehouse, right? It's the connection, the moment connection for the rafters. If this is just snug tight, what will happen is wind, for example, might blow on it. So there's like, I don't know, an extreme case like a cyclone or whatever. It will repeatedly blow on it over time and loosen the bolts, right? If it's only snug tight, like over like several decades or something. Say there's a cyclonic area, then this will eventually come loose and they'll be really dangerous, right? Because the structure could fail. So these have to be fully tensioned. So fully tensioned is the more extreme type of installation method, because when you fully tension it, it can't loosen. Essentially, it's kind of internally warped and fits in the groove of that connection, if that makes sense, right?
Wait, sorry, did you mean to like scroll down? Were you writing stuff?
Oh, have I done something wrong? Oh, no. It's I'm just like use my hands in real life to just talk, but I don't think you guys can see that. But
Oh, okay, oh good. I thought you were like writing something that wasn't on the screen.
Oh no, sorry. But I don't know. Does that kind of make sense? So you want to fully tension what you can see. This kind of moment connection should be fully tensioned, basically.
Yep.
Yep.
Now, for the case of this bracing, right, for example, does this need to be fully tensioned? Someone want to have a guess?
Sure. Yes, it requires to be fully tensioned.
Not really, because for shear bolts, they just need to be snug tight. The consequences of this failing is way more minimal, and yeah, to some degree you want this specific connection to be pinned, to act as kind of like a truss member, I guess. I might just be speaking out my ass at this point, but
No.
this one doesn't need to be fully tensioned. It just needs to be snug tight. It would be kind of overkill to make it snug tight, essentially, just because it requires more effort to fully tension it. I think you need some kind of like a specific machine to come around and do it. And if you need to do it for every bolt in a warehouse, it's gonna take forever. Whereas for snug tight, it's like a tradie with a power drill or whatever can get it snug tight.
So for shear force in general, you don't need to have it yield?
Shear bolts, yeah, generally shear bolts, you don't need it to be fully tensioned.
Oh, okay, yeah.
Yeah.
Just one last second then. So you have your shear bolts, and then you also have your fasteners. The fasteners usually are the ones that you open tighten. Is that correct?
Sorry, I missed that last part
or
of the sentence.
Or does it depend on do you open tighten for the fasteners, or does it not matter? Like it only depends on the joint type, like whether it's a pin joint or it's something else.
Sorry, I'm not really understanding the question.
No, that's fine. You'll probably cover it as we go.
No. I want to answer your question. I just didn't catch parts of it, I think.
As in, so the example you just showed us, that was regarding like a pin joint type or a shear bolt, correct?
Yeah, I'll just go up to it.
Yeah. And with those, you typically do snug tightening.
Correct.
But in that example, if instead of using like a shear bolt, if we use a fastener, would it be acceptable to, I guess, over tighten, or it wouldn't matter? It's just like depends on like what the situation is.
So remember, bolts and fasteners can be interchangeably used, like as a word. Are you talking about if we made this fully tensioned?
Yeah, that's correct.
You could. Yeah, it's just more a matter of like this is usually a repeated thing throughout a warehouse, right? These kind of connections, like say a warehouse has like 200 members, right? It might have like 2,000 connections, right? So that time that you invest in fully tensioning each one would just be a waste, essentially. unless you have to do it, which you do for axial connections, right? Does that make sense?
Yeah, that makes sense.
There's nothing wrong with fully tensioning it, like structurally, as far as I can see. It's if you did it the other way around. If you made this snug tight, that would be dangerous, like the axial one. But this is more like bolt design, I guess. For anyone watching the video and you can see my webcam, my light in my room just randomly turns off every now and then. It'll turn back on. It's just fucking weird. Okay, don't be caught off guard in this course. So for bolts, our phi value is 0.8. Okay. Except for ply and bearing, which is 0.9. That's another action which we'll get to. But yeah, because for the entire course, for all the member design, you've been using phi is equal to 0.9. Now it's 0.8, so just don't be caught off guard, please. Okay. Sorry, I'm gonna have to kind of speed up because I don't want this to go on for too long. So here's the formula for bolts and shear, right? It's to do with your ultimate strength, which we talked about. There's a reduction factor for 10.9 bolts, but we said that those aren't in the course, so don't worry about it. It will just be 1. There's a reduction factor for bolted lap connections, right? So that's like what you can see there on the right. If you have if you have a bunch of bolts in series and the lap length is too long from the first bolt to the last bolt, essentially you have to reduce the overall strength of it because some of the bolts, if they're being tensioned, are going to be touching, like are going to be correctly like aligned and doing what is supposed to be done in shear, right? Which is contact the hole's edge, right? If that makes sense. So like say this member's being pulled that way, the bolt is kind of like crushing against the that ply of the member, right? But if you have multiple of those in a row, they're not all going to be equally contributing to that, right? Just because of small manufacturing errors, right? And so when you have a long enough lap length, then you have to reduce the capacity. Okay, and then so we have this thing which I tried to explain, which is to do with your core area and your shank area, and it's to do with you have multiple plies, right? This is quite an extreme example, right? Just pretend it looks like this. You have 4 rectangular plates that are all like lapping over each other. It's kind of like if all of us put our hands together, right? And did like one of those like celebration things, like whatever, right? That's what it looks like. And so side on, it looks like that if you chuck a bolt in the middle, right? And so there's 3 shear planes going on, right? 1, 2, 3. Yeah. Now 2 of these shear planes are intercepting the threads. The threads are the screwy part, essentially, right? And 1 isn't. So that's what NX and NN are. It's a number of shear planes intercepting the areas with the threads and the areas without the threads. But it doesn't matter because all we care about is a number of shear planes, and we always assume it has threads to be conservative in this course, right? And so yeah, you're just counting the number of shear planes and then multiplying it by the core area. So core area was a smaller area here, right? And then shank area is the bigger area there. Yes, okay. So for bolts in tension, right? So that was shear. That was bolts in shear. Bolts in tension. This formula is a bit more similar. The formula is a bit simpler, I should say. But we use something called AS, which is basically in between the core area and the shank area. Shank area is AO, core area is AC. AS is a number that's in between there, and it's almost saying like, okay, we're gonna treat it as if it has this kind of area and it's a cylinder the whole way. Well, not the whole way, we just need one cross section. But that cross section that we take is AS, right? Now this is just given in a table, but you just be aware that you're gonna need another line, right? Sorry, you're gonna need to look at a separate row on this table as opposed to core area and shank area. Am I making sense so far? Is this okay?
Yeah.
Okay, fantastic.
Yep.
This 90% of the time, I want to say, maybe not 90% of the time, 80% of the time, it doesn't matter because we just need to use this design table, right? Which gives you the answers already. When I say 80% of the time, what I'm talking about is if you only have one shear plane like this, right? If you have one shear plane for the shear values on this table, so that's single shear it's called, then you can use this table. Oops, what have I done? But if you have multiple, like that example I was talking about with the hands in the middle, then you can't use this table anymore. But these will give you the value for phi VF, and it's already factored, right? They've already taken 0.8 as the factor, so don't double reduce it. Do you know what I mean? But yeah, does that make sense? And then it'll tell you in the question whether it's snug tight or fully tensioned. Keep in mind there's two types of fully tensioned. TB means the bearing type, and F means the friction type. And there's nuances there, but it's in my notes above, but I'm not going to go into it just because conscious of time. Okay, make sense?
Yep.
Fantastic. Then we do tension and shear if our bolts are in tension and shear together. I'll be honest, I cannot think of an example right now off the top of my head to illustrate this, but yeah, say your bolt is taking axial forces and shear forces at once. They're going to be weakened. It's similar to your assignment. Do you remember how taking shear and moment at the same time? If you remember, there's a formula to reduce the capacity that it can take, right?
Yeah.
So this is a combined check for shear and axial tension for bolts. That's what this is. In practice, I've never used it in this course, and I've never used it at work either. But just know that it exists. Okay. Next, I'll talk about ply and bearing. So when you have kind of a thin rectangular plate of some sort, you can call it a ply, right? Or even like a flange or a web, you know, like any kind of rectangular plate, it can be called a ply. So ply and bearing failure is a little bit different to bolt failure. So you remember how before you have, I'm not going to draw like the members which are being connected together, but imagine you have your bolt and then it's being sheared like that, right? So that's shear failure of a bolt, right? And then say we have the bolt is being pulled, right? This is axial, or I guess it's called axial because it's compressing in two members together, right? Now this is tension failure, right? That's the bolt failing, right? That's the bolt ripping in half in shear, or becoming like spaghetti and eventually just snapping like that in the middle, right? For tension. So ply failure is a bit different because in this case this is compression happening on it. It's if the ply breaks, so the thin sheet of metal breaks rather than the bolt. It's still considered a connection failure, but it's to do with the ply failing rather than the bolt. The bolt can be fully intact, right? Similar for this is ply tearout. So that's if your bolt is near the edge of a ply, and there's not very much. I don't have a better word for this. There's not very much meat on here, right? And so it could have essentially just tear out. That's what a tear out failure is, right? Here I've got an example actually from work. It's where you have the bolt hole, right? So this has the bolt on it, you know, and then next to it, we have an empty hole, right? And so if there's tension acting on this member, yes, if we have tension acting on this member, the bolt could essentially just slip like that, and then you have this big gap and it's all loose. The bolt's just useless, right? Make sense?
Yeah.
But yeah, that's tear-out failure. Bolt groups, right? So this is more like I told you about pretty much everything that can happen to a bolt, but most likely, and this is the most common kind of thing you're designing for, you're more just designing for a bolt group, right? A bolt group means several bolts at once, and there's a bunch of formulas related to it, and that's actually where the course is going. So you have to find the centroid of the bolts, right? And this is a bit different to, do you remember how, like, say you're trying to find the centroid of an I-beam like this, right? You would do, centroid is equal to sum of area, what am I doing? That. Yeah, just trying to find, like, where the centroid is on the y-axis or whatever. You would use this formula or something, right? That should look kind of familiar.
Yep.
Do you see how the one on the left looks different?
Yeah, it's missing the area.
Yep.
It's because bolts are considered a single point in space, right?
Oh.
Whereas these are considered not only points, but points with an area, right? Like your elements of a I-beam or whatever. So all the formulas that you see are going to be different. You're not going to be used to these formulas, right? So let me show you, for example, right? Moment of inertia, right? For an I-beam should look like, BD cubed on 12 or whatever, right? Without parallel axis theorem. But here, it's literally just sum of y squared. And that's a result of the fact you're dealing with single points in space. So just be really careful when you're analyzing these, like when you're writing these formulas down. I made like a bunch of mistakes. I had to correct the notes before I made this because I kept writing these formulas wrong, specifically like this one and the one for the welds, right? There's plus signs, there's minus signs, there's shit's just moving around. Just be really careful, yeah.
Yep. So is it just the coordinate sort of squared for ix and iy?
Yep.
Okay.
The bold formula is not too bad. The weld formula is where it gets trippy, because welds are straight lines. So that they're one-dimensional. So area is two-dimensional, right? Welds are one-dimensional. Bolts are zero-dimensional, because they're single points in space, right?
Yeah.
So that's where it gets a little bit confusing. But yeah, you'll see kind of all the formulas and all kind of start to make sense. Sorry, I'm hearing a little bit of background noise. Can whoever has that just try to mute, please?
That's from me. That's me.
All good. So that was. You remember how we talked about shear bolts? So this is shear. Shear bolt groups, or in plane action. So that you're only gonna be dealing with shear V, right? Now, for this course, I think this is a little bit rarer, but at work I've done this a little bit more. So, do you remember the haunch connection I was talking about, right? Sorry, I shouldn't say the haunch connection. The splice connection, it's called, where we have the axial bolts like that, connecting two rafter beams, like that. These are your axial bolts, and say there is moment happening on this, like a rafter, right? We're making sure that the outermost bolt, say looks like that, so there's multiple bolts. We're making sure that the outermost bolt in tension doesn't rip apart, essentially, right? And this is assuming like the centroid of the bolts is the neutral axis. So the bottom one is in the same magnitude of compression as the top is in tension. Do you guys hear fireworks? There's fucking fireworks outside.
Yeah, I'm hearing that.
Yeah, anyway. Interesting. But what they do in the slides is they pretend that the neutral axis is off center, right, by amount of d over 6, because then it exaggerates how much tension is in this bolt. More tension, I should say. But yeah, anyway. You guys probably have heaps of questions, but yeah, are you guys kind of following? That's what I'm more interested in right now.
Yes.
Okay.
I roughly get the idea of things.
I think it'll make more sense in a question, 100%.
Yeah.
That's probably why, because yeah, right now it's all just makes no sense.
Yeah, because with the D6, I'm guessing they just kind of came up with that. Like what?
Yeah, you know what? I don't know where that comes from.
Why?
But it is conservative because D on 2 would be the middle, right?
Yeah, true.
So D on 6 is just saying like a considerable offset from the center to consider the neutral axis.
Okay, yeah.
Someone came up with that, I don't know.
Yeah.
That's what's in the lecture slides, so I would follow that, and that's what they told me to do at work. Do this assumption rather than the middle, because this middle one is too. It's not accurate, I think. Yeah, it's pretending that it's better than it actually is in reality. Okay. So, next we have an example. So, you see this bolt group here, right? The first thing we have to do is we have to find the middle of it. And for this specific arrangement, it's actually really easy because you can literally visually see where the middle is, right? And that's like half the battle, just finding where the middle is for a lot of these bolt groups. Because sometimes your bolt groups can be really weird. They can be like, I don't know, that or something. And then you have to do those centroid formulas, and then you have to set up like an axis here as a starting axis, and then once you get where the centroid is, say the centroid is like here. Now this is the new axis, do all your calculations from that. But if you can visually see where the middle is, you immediately set that as your coordinate system. Yeah. And then the calcs work off of when you set the centroid as the coordinate system. It's sometimes called ICR. That's the instant center of rotation. You guys probably haven't heard that since like 1300, but yeah, just that's the same thing as the centroid for bolt groups and welds, right? Okay. So basically we have a force here that's applied off center to this this is like, we're doing shear design, correct? Do you guys agree?
Yep.
What we're gonna find is this is gonna cause a moment, right? This force is off center. It's gonna cause a moment that makes all these shear in different ways, in different magnitudes, right? So this is V star F for bolt 1, let's call that. This is V star F for bolt 2. Do you get what I mean? So they all have different magnitudes. And what you're going to find is that the ones that are further away from the instant center of rotation have a greater magnitude. I might exaggerate this by a bit. Does that make sense? Usually the one that's furthest away has the greatest magnitude, but it depends on the numbers. And since we have 4 that are equally far away, then those should have the same magnitude in theory. Okay. Have I lost you guys?
Nope, I'm on board.
Okay, fantastic. So
No, you're doing fine.
Oh, fantastic. Okay, eccentricity, right? Have you guys heard that term before?
Yes.
So if you have a Y force, right, let's just think of 1300 for a second, right? We have a y force, and we want to take the sum of the moments about this point, right? Yeah? This is, let's call it F, right? We have to find the perpendicular distance D. That's your lever arm, right? So similarly, we essentially have this as your eccentricity, and the eccentricity is perpendicular to that force. So if this force is like acts in the y-axis, then this eccentricity acts in the x-axis perpendicular to it, right?
Yeah.
Yeah, cool. That's essentially what we're doing. So we're taking the sum of the moments about here, and we call that m star O, I think. Yeah, here we go. So m star O is that force multiplied by ex, which is the lever arm. So this is a little bit of a, oops, pretend you didn't see that. How do you find ex based on these numbers?
Don't you just use like the 200 plus the 70?
200 plus 70?
No, wait, sorry. It's...
But then we don't know what this distance is here, right? Sorry.
Yeah.
So you're missing whatever this is.
Yeah, that part.
Anyone want to have a crack before I spoil it? Okay. If I go to
310 UC. Oh my bad.
No, you're right. Go on. You're on the right track.
Like the 310 UC doesn't it tell us the length of the the pod, something
Correct.
like that?
No, you're 100% right. So
Okay.
the way it works is when you specify a UB, right? Say a 610 112 UB, right? That first number is always the depth. This is for a universal beam, right? In reality, it's not actually that. It's like, if you look on one steel, it's probably like 111.5, I don't fucking know, something like that, right? But it's pretty close, right? The second number, this is your linear mass, kilonewtons per meter. That doesn't really matter as much in this course, but it's a good way of gauging how expensive the steel is, because the heavier that your steel is, the more expensive it was to produce, right? So that's kind of, anyway. So the number you're looking at is the first one. So for a UC, sorry, I didn't finish my point. For a UC,
okay,
it's both the width and the depth. Now again, these numbers are slightly different to 310. Like in reality, there'll be something slightly different. But yeah, so that's the way you find it. So if this entire thing is 310, right? Half of it is that length that you want, right? It's 155. Make sense?
Yeah.
That's just a little trick that they put into this question for some reason. But yeah, that's one way you can work it out. Cool. Okay, so yeah, you find the centroid, that's step one. Then you set the coordinate system at the centroid, right? So that's what I drew here. You wanna set that as your x and y system. You determine the eccentricities of any forces, and then we calculate the second moment of area in the x and the y direction. That's just a matter of summing y squared and x squared. Polar moment of inertia is adding the x and y together. At least for bolts, this is different for welds. And then you just chuck it into this big fat formula. But here's the thing. It might be worth doing it as a table. So we just need the worst case, right? We just need the worst case bolt. But how can you tell whether bolt 1, 5, 4, or 8 are bigger, or like any of these, right? How can you tell? Generally, it's the one that's furthest away, right? So it could be 1, it could be 5, it could be 4, or it could be 8, right? But we don't know. It depends on what forces you have, right? And so we found 5 and 8 are actually the biggest shear forces. That's these two. Okay, so these will have the greatest magnitude of shear, like that, and maybe like that, and there's V star F. Okay, everyone following?
Yep.
But then when you get to the point where you have to find the capacity, it's literally just a matter of reading off the table, and like that. So that's what I mean by the capacity is really easy to find. It's the external force that's hard for bolts, right? Cool. That's bolts. I'm gonna try to quickly talk about welds because I'm conscious of the time. Welds, a thing that's hard about welds is phi. So phi isn't just 0.8 for, like in bolt for bolts is 0.8 for everything, 0.9 for ply and bearing or tearout, I think, one of those two. For welds, it depends on the type of weld essentially, right? So let's quickly talk about the types of welds. Loosely, there's two types, right, that are kind of umbrella ones: fillets and butts. So fillets join two members, usually at a 90-degree angle, right? And butts join two members kind of like end to end, or generally there's like a little V-shaped opening that the weld kind of fits into. So you know that thing I was talking about. Say we have two square hollow sections, right? We're trying to marry them together. What you would probably do is you would do a butt weld at each of those edges, right? Okay. Weld quality. There's general purpose welds, and for all of these, the phi value is 0.6. Special purpose, more expensive, right? But they have a more higher phi value essentially, right? So higher capacity. Complete penetration butt welds, like I've shown, and incomplete penetration butt welds, you can just see kind of like what they look like. They're a bit different. You can just see from the picture. So, but the important one is we're going to do weld groups in these questions, right? And that one has phi is equal to 0.8, assuming that it's special purpose, right? But if it says general purpose, you use 0.6. Electrode designation. So when you're welding, you're gonna use a different material, right? And it's similar to like bolt grades, right? We have electrode designations, right? And the two most common ones you'll see in the course is E41 and E48. The good news about these is it directly corresponds with the strength values. So sometimes they might not even give you FUW because it's implied from the electrode designation, so just be careful for that. Yeah, so the value we're using for capacity is whatever the electrode designation is times 10. Everyone following?
Yep.
Fantastic.
Yep.
Okay, here's a bit of terminology, but the two you really need to know is the leg and the throat, right? Pythagoras triangle, right? Basically, the hypotenuse is the throat, and these are the legs, right? And I bring up Pythagoras because you literally need to use it, but you use it this way. Oh, sorry. Drawing this weirdly. How do I draw this? It'd be more like this. Oh no, what have I done? Sorry. My bad. This is a leg, and there's two throats. Even though there's actually only one throat. Okay, it's a bit confusing, but we kind of mathematically we consider it the other way around because I think it makes more sense. There's a leg. There's the leg. That's another leg. That's the throat, right? So the throat is actually the smaller shape. This is almost like a year 8 maths puzzle, right? Because we have throat, and the leg is actually the big one, the hypotenuse, right? Make sense? But physically, we have two legs and one throat. Okay, hopefully that makes sense. Fuck.
Right.
Yeah. Anyway, there's formulas for the minimum and maximum size that a fillet weld is allowed to be, right, along an edge. So it's based on we have 2 pliers, right? Say we have 2 pliers like this, 2 members, and they're being welded together. Have this fillet weld, right? And maybe you have a fillet weld on the other side, who knows? If we're looking at that side on, right, that's what this looks like, right? So that top member, right, the one that's sitting on top, let's kind of draw this the other way. Anyway, you get what I'm saying, right? That plate thickness is T, right? You know what? Actually, wait. Sorry, it was bothering me. It's like this. That's the weld that was under. This is the weld that's on top. Okay, that makes more sense. That member has a thickness T, right? Whereas the leg has a thickness of TW. TW is the weld thickness, I guess. Sorry, the leg of the weld. There's some rules for what the minimum and maximum is allowed to be. Okay, so welds, right? We just do shear design for welds, okay? And unlike for bolts, there's not a table for it, right? Because this is more things that depend, right? Like the throat thickness is not standardized. You have to design for like a throat thickness, whereas bolts come in standard sizes, right? The other thing to note about welds is that you do everything in terms of kilonewtons per meter, right? And this is also kilonewtons per meter instead of your normal. You know how for member design we usually do something like this, right? This is in kilonewtons, and this is in kilonewtons or something, right? Or newtons maybe. For welds, we do it per linear meter, right?
Oh, yeah, okay.
Because essentially we're saying like it's shearing V star amount, right? Per meter. Kilonewton per meter. Because it's all linear, right?
Is the meter assumed? Like per meter?
It's like in geotech. When you're designing a strip footing, you just design everything per meter.
Yeah, okay, yeah.
Yeah. You could also do it in newtons per millimeter. I can't remember what the question does. Maybe we'll see in the question.
Okay.
But for weld groups, right, I've just put some dot points here that I want to run through because I think this is the simplest way to explain it. So each weld line has a centroid, which I've drawn as a blue circle, like here, right? The weld group overall, so all 3 of these welds that you see here, has a centroid. That's the ICR, right? Instant center of rotation. We want to find this ICR and set our coordinate system there, right? But what we usually have to do is set it to a known point first in order to find the ICR, and then we start doing the calculations from the ICR, which is how you're supposed to do all the calcs, right? And we also have to calculate MO, which is the resultant moment at the ICR. And you do that by summing the moments about the ICR. So if all your forces and moments were over there, you have to find the eccentricity and set it back over here to where the ICR is. I just said a bunch of like acronyms and shit. Are you guys kind of following?
Yep.
We just move everything to the ICR. That's the bottom line, right?
Yep.
So in terms of a step-by-step, it's like what I said. We have to start with a known coordinate system. Here I've started in the bottom left, right? Which is marked in red. Then we find the ICR, and we set the new coordinate system there. So that's what's in purple, right? Done. Then we find the eccentricity of the loads, right? Same thing as before, right? So you find the lever arm, the perpendicular distance to this force, find the perpendicular distance to that force. That's the eccentricities, right? And we find the resultant X force, Y force, and moment, right? Those three things. Here's where the formulas start looking whack, right? So polar moment of inertia has this weird formula for Welds, but we need the polar moment of inertia. We don't need Ix, we don't need Iy. The only reason we needed those before was to find IP, right, for bolts. Here we can directly find it using this formula. So this is your linear polar moment of inertia formula, right? And using this formula we can find, that should be a lowercase, we can find the weld, like the shear per unit length at any point along the weld using this, right? So given that information, right, do you remember how we said before for that example with the bolts, right? The ones that are furthest away from the centroid, like here, that's the centroid. The ones that are furthest away are the ones we have to check, right? Because they're the worst case scenario, right? Now for a weld, say the one that we drew before, I'm doing blue. And that's the middle here. Where do we have to check? Do we check the centroid of the lines, do you reckon? Centroid of the lines being here, here, here. Where do we check?
Would it not just be like the fringe cases, like at the extremes, like at the end of the weld itself?
Exactly. You're exactly right. That's what we have to do. So we set these corner points as A, B, C, D, because that's where the worst shear would be, right? So if I were to draw this, right, for example, say the worst shear is here, and then it gets a bit better, then it gets a bit better. I'm exaggerating this. Might be okay here, might be okay here. Here's alright. It's quite small. It's quite small. Maybe it gets bigger again here or something, right? But it depends on what your moment is and what your forces are, and you know. So check the corner points, so the extreme points, right? And that's it. And you find the capacities using the formulas from before, but the formulas weren't that hard. Yeah, actually I might I might export another copy of my notes, because I got a bit lazy. I wrote capital V for a lot of these. It should be lowercase v. But yeah. Yeah, everything's just laid out here. And just remember, you gotta find the throat thickness, so we have to use that reverse Pythagoras formula to find the leg lengths, right? And yeah, and here we were finding the maximum force that was allowable for this weld, basically. Okay, any questions?
A bit curious, you know, like the IP formula for the welds?
Yep.
It has the x squared plus y squared. That's the same as the bolts, right? Because the Ix was x squared and the Iy was y squared. and the IP for the...
Yeah, you're right. Yeah, you're right. So the difference is that we consider length. Yeah, everything's to do with length because it's one-dimensional.
Oh, yeah.
But yeah, you're right, pretty much. But then there's an additional component for there's this additional component here basically for IP in one dimension. Because if you have zero dimension, right? That's the bolt case. Then you're just doing this part, right?
Yes.
Yeah.
Cool.
Yeah, I'm trying to think.
Also, the table that you refer to with the shear values,
Yep.
would they always give, would you always get cases that are actually in the table, or can you get stuff like that's outside the table? I mean, the values.
Oh. So think about it like this, right? There's there's actually heaps of grades, but so there's 3 reasonable grades that it can give you, right? And they already said in the course, at least when I did it, they don't do 10.9 bolts.
Oh, okay.
So you're already left with just this and that, right?
Oh, okay. They give it to you according to the grades. Okay.
And then there's only so many bolt sizes that are manufactured, right? So think about it like this, like you go to a Lego store. They're not just gonna give you a fucking piece of Lego that's like 50% bigger than another Lego because it's not gonna fit, right, with the other Legos.
Yeah.
Same thing with bolts. There's standard sizes because everyone uses those sizes, the universal sizing. So that's what like M12, M16, M20, M24, M30, M36 is. They're not gonna give you numbers outside of that.
Yes.
So realistically, this is pretty thorough. Yeah, this table.
Okay. Yeah.
Yeah. That's why you can use the table for bolts, but not really for welds. You can't. Each weld has a different thickness, and it fucking just depends, right?
Yes.
Okay. Yeah. Any other questions, guys?
All good.
All good. Karan?
I am good, my good sir.
Okay. Thank you very much for joining me this week. And yeah, I mean, there's one more week, but if you guys are free, then feel free to join that. If not, yeah, but they'll be recording another way.